Okay, hello, welcome everyone. It's a pleasure to have Dana Rahbani as a speaker today in the seminar. Dana did her bachelor from the American University of Beirut in 2015, and then she came to Zurich to do her master in biomedical engineering. So actually we were in the same batch for our masters actually. And then she started doing her PhD in 2017 at the University of Basel. And today she will be talking about her MICAI 2021 paper, where they do a Gaussian process. They use Gaussian processes for anomaly detection. So looking forward to the talk, Dana, and the floor is yours.
Thanks, Nirav. And thank you everyone for joining. If you have any questions or comments, please go ahead and ask them while I talk. And I will start by talking about this presentation is based on our MICAI publication recently, Sequential Gaussian Process Regression for Simultaneous Pathology Detection and Shape Reconstruction. And I'll start by giving some motivation from the data that we're working with. So usually we have such meshes. This is a part of the cranium which has been extracted from CT. It's in 3D, and you see that some parts of it are missing. So there's some teeth that are not there, and also the condyle part of the mandible. And what we want to do is get a reconstruction of the healthy shape, so it would have looked like if it were healthy, as well as a label map. And this you see here on the right. So I've indicated in blue the reconstruction of the parts that do exist on the target, and in red the parts which are pathological. So again, to be able to get this, we need a combination of two methods, basically. The first one is how to get the healthy shape. So what prior are we using? And this is in the form of a shape model. And then also a method to get the pathology label map. So this is an unsupervised method where in the beginning you only start with this target, and then at the end you have the segmentations as output along with the reconstruction. So I will start by talking about the shape model that is used in a bit of literature and background, and then I will talk about the proposed method and some results. So the shape model we use is a Gaussian process morphable model. What this means is we have a reference. Here I stick to the mandible example, and this reference defines the domain on which we have some data. So this domain over here would be the set of vertices which are making this reference and the connections between them. On this reference, we can define a set of deformation fields. So this deformation field is a sample from a Gaussian process, this one over here and this one over here. And what this means is we have a mean deformation field, and we have a kernel which defines how the different vectors relate to each other. And we can take different samples from this Gaussian process and apply them onto our reference, and we end up with new samples. And for them to all be valid instances of a mandible, we need to make sure that this deformation field is actually learned from mandibles. So this is how it's equivalent to an SSM. You have a set of mandibles from which you can find a covariance matrix that determines this deformation field. And then we learn from that a Gaussian process, and we can take some samples from it. So basically we apply on our vertices X, on each one of them, we can apply a deformation vector, and the whole field is a sample from a Gaussian process. And this is similar to an SSM. Here you see the low rank decomposition of the GPMM. It basically consists of a mean, which is the mean deformation field, or a 0, 1, and we add to it a set of deformations like we do with the statistical shape model. So this, the eigenvalue and eigenvectors are obtained from the covariance matrix, and we can move along them by changing alpha. What this means is if we have a mean value, we can change alpha, let's say, of the first principal component. And once we decrease it, we observe that alpha -1, the mandible will look like this, -2, it will look like that. And so this is how we can generate new mandibles from our model based on the Gaussian process. And we can also, instead of only generating some samples, we can, for a new target, find the alpha that describe it. And this is usually written in such an optimization process problem where we have a target shape and we have a reconstruction, which is defined by alpha. And so we try to find the alpha, which give us a sample which is as close as possible to the target. And instead of writing this as an optimization problem, we can also use the Gaussian process to get the solution. So basically, given some observations, which are U, deformation vectors, we can update the model to take into account the observations. And so we have a new mean and we have a new kernel. And the mean is actually the same solution that you would obtain in an optimization problem on the left. And so this closed form predictive posterior distribution can be used once you have some observations to get the alpha, which represent a new sample. And here I show the problem if you just run this on a target that looks like the first one I showed. Because it's missing some teeth and because of the outliers and pathologies that are here, if you just run a regression on that without removing the outliers and without doing anything robust, then you will end up with a surface that does not look correct. And here I have an overlay of the two. In green is the target, and in white is the regression overlaid on top of it. And you see, of course, in the pathology region where we have no information, there are obvious deformations which are not correct. But also this influences the inlier region. So even where we do have the teeth, and here you would expect the model to fit, you observe some incorrect reconstruction in the teeth region. And this is because the whole model is trying to fit to what it observes, and this is not the case. So we have some points on the target which have no corresponding points on the model, and we need to inform the model of that and remove them. And this is basically the outlier problem. And here I show two different types. You have a bump. So if this is a mandible, which is the full reference, you have some target with some deformations here, or you can have a whole type of deformation where the target is missing some parts. And in both cases, the problem is that when you try to perform regression on a target that has such outliers, you cannot rely on the assumptions you usually use on the residual model. So usually we say the residuals are Gaussian distributed, and we try to minimize the value of this residual. But with the bumps and holes, we cannot anymore because we do not know what the value of the residual is. So there is no point in this whole case. You do not know what the actual point is on the target, so you cannot compare it to the current reconstruction and obtain a residual value. And that is why we do not know for the outliers what the distribution of the residuals is. And this causes a problem for the closed form predictive posterior distribution. And this problem actually is called outlier detection in general, and people use it when the pathology class cannot be modeled. So for example, the holes which I showed before are not always the same shape. They don't always appear in the same location. You can have some targets which have both hole and bump. And so you cannot expect to model this pathology class, but you do know what the normal data set looks like. And this is from the shape model. So we do know what mandibles look like. We can learn from a set of mandibles a shape model. And what outlier detection tries to do then is to use this normal data set to detect what is abnormal. And this is the second step here. So we use the normal data, we learn a model about that, we compare the abnormal data to it and try to classify. And these methods usually need a threshold. The threshold can be on the residual errors or average distance. It can be learned or it can be imposed in the beginning. And also they need a reconstruction method. So how are you going to obtain the regression of the mandible in the case that we're talking about so that you can compare the data to the threshold? And this probably sounds familiar because already different methods in the literature that do pathology segmentation all can be formulated in terms of outlier detection. So for example, here with the GAN, from Anugan 2017, the main idea is you have a GAN and you train it on healthy data, here just 2D images. So at the end, you expect that your generative adversarial network will be able to reproduce this healthy data that you give as input. And then once this training is complete, you give as input an anomaly data. So basically an image which has some pathologies in it. And if the model is good enough, then it will be able to reproduce the image as it would have looked like without the anomalies. So then when you subtract the generated image from the input one, you will have some residuals, and these residuals are going to represent the anomalies. And so basically the threshold in this case is the residual errors. And if you train this model, you can see what the distribution of residual errors is for healthy data, let's say 0.1 average distance between the target and the reconstruction. And then once you have an anomaly map, anything above this value 0.1, you would label as pathology. And the reconstruction is based on the entire image because the GAN takes the entire image regardless of where the pathologies are and if it has any, and produces another image. More recently is AskNet, which is also similar to AnuGAN, except that now in this case, it actually produces two outputs. One is the healthy image as expected from the GAN in the previous case. The second one is a pathology label map. And then this paper, they introduced different loss functions in order to make the two images as distinct as possible from each other and improve the reconstruction quality. And in order to, at the end, obtain a threshold, this is done based on histograms. So they combine the two images and they expect to have 3 distinct peaks when you do a histogram on the pixels of this image. And then from these peaks, you decide what the threshold is. And so the reconstruction in this case is partial because you do separate into 2 different types of data, so the anomaly and the healthy, but the threshold requires a bit more manual input. And similar stuff has been already done also with shape models and also in the mesh domain instead of images. So for example, in robust moving least squares fitting here on the right, you take some observations and you fit to them, here in this case, just a linear fit. And then you use the regressed line in black to classify whether the pink points are close enough or far away enough. And then if they're close enough, you assume they're inliers, you include them in the regression and you update. So this is also a partial reconstruction strategy, but the threshold is also based on the residuals. It doesn't really consider that what the value at this pink point is. And so there's, I will now talk about the proposed method, which also does partial reconstruction, but with shape models, and then has a dynamic threshold value, which is not learned in advance. And
sorry,
yeah.
Can I ask about the difference between partial and full reconstruction here?
Yeah. So what I mean by that is, for example, with the GAN, you give as input the entire image, and you expect the GAN to generate the entire image again. So you do not label on this input image different regions to reconstruct. While here, for example, with this sketch, you choose a subsample of the points and you reconstruct based on them. So this is more like a ransack approach, where if you think some of the data over here is corrupt and you do not want it to influence your reconstruction, you take a subsample from it and you perform reconstruction on that. And then the hope is that this reconstruction will be robust if you choose the correct subsample. So you can repeat this with different subsamples, you will obtain different reconstructions. And the main purpose, so the motivation behind having such a partial approach is because you do not want the outliers to influence the regression results. And here you would need to have a lot of trust in your GAN if you give it an input image and then it will generate, if you give it an input image not from the expected domain that you've trained on, and then you expect it to still perform similarly. And so the partial ones try to solve this problem. Yeah.
And sorry, was there something? So yeah, that's very interesting. And in the image case, it would then mean we can block out some parts of the image and try to reconstruct the image, hoping that the parts that we blocked out, if they were indeed the anomalies, then we would be able to reconstruct the healthy part correctly. Is that somehow correct? Okay.
Yeah, that is correct. This is, I think, how I understand this paper as well, because instead of only going through the AnuGAN, which just goes through like this and ends up with a reconstruction of the healthy, you explicitly expect it to also model whatever it is that is not in the first domain of healthy shape. And then they expect this over here to improve once you include the pathology reconstruction as well. Because you're telling it that not everything in this image is expected to appear over here.
I see. Okay, cool. Thank you.
Thank you. Okay, so I will continue with the proposed method based on GPMMs. The main idea is that this is a sequential Bayesian optimization approach where we start with some observations which we assume are correct, and these can be clicked by the user or provided in some other way. And then we perform shape reconstruction on this inlier region. Based on the reconstruction, we decide what new observations to include. So we start with some landmarks clicked on the mandible, for example, and then we grow in regions around these clicked landmarks and decide what is the next part of the target that I should reconstruct. And then we iterate between the two, and eventually both the shape and the label map will improve. And so the proposed threshold is based on different things. Instead of defining it in advance or learning it from previous fits, we propose to learn it during fitting. And so you can take into account how good the landmarks have already been fitted, and also the observed part of the target, how likely it is that this is a healthy part. And I will explain it with a 1D plot, where here you see the deformations taken from a Gaussian process in 1D. So along the x-axis is the position of the observation, along the y-axis is the value, is the evaluation of this observation value using a sample from the Gaussian process. In gray, you see some samples taken from the GP. This GP has an RBF kernel, so it's not a shape model one, but just to show as an example now. And the solid black line is a chosen sample to reconstruct. Instead of observing the sample, we usually obtain observation values. So these are the dots over here, which are taken from the sample and have some residual noise added to it. And in the region between the two red lines here, I've introduced additional noise. So instead of only having a Gaussian noise to these observation values, I also shift them up, as you can see over here. So the goal would be to perform reconstruction using this GP to obtain a reconstruction which is as close as possible to the solid black line that ignores the values of these observations over here. And one thing I should still mention, the green shaded parts indicate how many standard deviations away you are currently from the mean of the current GP. So 1, 2, and 3. So now what happens is we have some observation in black over here. This I sampled randomly, just not within the pathology region. When we take this observation into account, we can update our Gaussian process using the closed form analytical predictive posterior distribution equation, which I first showed. And so we end up with a new mean, which is now here, dark green, no longer at 0, but shifted towards the observation. And we have a new set of variances at each point. So this is what you see here with the shaded green regions. The closer you are to this observation, because of this kernel that is defined, you will have a smaller remaining variance. The further away you go, you will have increasing remaining variance until you get back to what it was before conditioning. So now that we have our update, which is an updated mean and an updated covariance, what we can do is decide which new observations we want to include using this information. So we're trying to choose some points from which are the black dots over here, which we should use to update our model on next. And so we take this observation, we see how close is this observation to my reconstruction. So how close is the black dot over here to what the green function is predicting is the position of this black dot. And instead of just using the distance, we use the Mahalanobis distance because it takes the distance between the two and normalizes it by how much variance is remaining. So the further away you are, here the variance is quite big, and so the Mahalanobis distances will be smaller. And then we set a threshold based on these Mahalanobis distances, which we computed for the clicked landmarks. In this case, it's just one, so it will just be this one value. And then we look at all the other observations and we compute their Mahalanobis distance to the target. So we're basically taking this dot and we compute the Mahalanobis distance to where it locates here on the green line. And if it's lower than the threshold, then we include it to be used in the next update step. Otherwise, we do not. And the main difference between this example, which I show in the meshes in 3D, is that in meshes, we use also the neighboring vertices as another criteria. So these would not be included, but only neighboring ones. And then,
sorry,
yeah,
oh,
sure.
Another question. So I should think of each point in this 1D plot, I should correspond that with one point in the 3D mesh, right?
Not a point, but a deformation vector. So it's basically the point that is on the reference and what corresponding point you assign it on the target. And for that, you have a vector that connects the two to each other. And this vector is coming from a Gaussian process. So almost a point, but it's just the terminology that is a bit different.
I see.
Because the GPMM uses the deformation. So the Gaussian process is defined on the deformation vectors and not on points. So you can think of it as 2 points and the vector connecting them.
I see. One on the reference and one on the the test
yes,
mesh.
Exactly.
Right.
Exactly. And the one on the test mesh you get based on what correspondence function you decide to use. So it could be just you see what the closest point is, and then you have these 2 points. Or you can use something more complex, like if you use the curvature or so, but this would need more work. Yeah. So I just use the closest point on the target.
Okay, thank you.
Welcome. So yeah, now we have the points which will be included next in blue. We condition the model on them and we end up with yet again another mean in dark green and another set of variances expected at the remaining observations. And this we repeat iteratively. And you repeat this iteratively until at the end, no more new observations are included. And so basically with this method, the threshold that is proposed is dynamic because every time we have a new set of observations here in black, we get a new Mahalanobis distance and a new threshold, which we use for classification later on. And so it's not fixed and you learn it during fitting. And it makes use of the uncertainty because we're making use of the remaining variance in the model after conditioning on some observations. And it's a region growing approach because here it does, oh, yeah, Nirav.
Sorry, what is the PC here in 0.3?
Oh, yeah, so this is a percentile. I will talk about it in a bit, actually. It just means, so in the paper, we had phrased it with confidence intervals, but it's almost the same thing. So if you have a bunch of observations, you have to choose either to take the average of them or to take the maximum, like how to get the threshold from this list of Mahalanobis distances. And what we use is a percentile value. So let's say 65 percentile. So you sort them and you take the 65th percentile. And this is equivalent to looking at a confidence interval. I will show in the next slide how. So how it works is here, this is what was in the paper and it's from 3D. From the 3D case, not the 1D case. And in blue, you see the Mahalanobis distances of what is currently classified as an inlier. So the observations which have been used to update the model so far. And in red is the Mahalanobis distances of all the other points. And what we did was because this is a skewed distribution, we took the logarithm of it and you end up with something that is roughly Gaussian. And here in this roughly Gaussian distribution for the inliers, you can define a confidence interval. So you can say you want to see what the upper bound of the 30% confidence interval is. So you go 15% above the mean, and you end up with this threshold in black. And so this is how the confidence interval is obtained, but it's the same as thinking of it as a percentile in this space over here. And the QQ plots show whether something is truly Gaussian or not, basically. And this QQ plot is for the blue inlier distribution here. So the blue logarithm of Mahalanobis distances of the inliers, and it's roughly linear, but not 100% linear. Yeah, so that was it for the method. I will talk a bit about some synthetic experiments to compare to other reconstruction methods, and then some challenge results. So for the synthetic experiments, we also used the mandible, and we randomly took out some vertices, and these are of different sizes and randomly located across the mandible. And here I show an example one where some part has been taken out, what the reconstruction is with the predicted label map and an overlay of the two. So when you see this mix of blue and white, it mainly means that the two surfaces are overlaid on top of each other. And this here is the reconstruction. So for the synthetic evaluation, we compared to ransack, which is the method where you randomly take some points on the target and you fit the model to them, and you then take another subset of points and you repeat this multiple times. CPD, which is a probabilistic registration method. ICP for point sets. ICP, which is iterative closest point algorithm, a non-rigid version of it to perform the non-rigid registration. And FSSM with IP, which is like sequential GP, but a sampling-based version, also developed by someone in our group. And what you see on the x-axis is the outlier ratio, so how much of this target has been removed. And on the y-axis, you see the average distance. And for each one of these outlier ratios, we have 10 different samples, and the average is basically the average of the 40 samples. And you see for the distance, for the big outlier ratios, then it is with benefit to use a method which iterates between finding a label map and doing a reconstruction. For small outlier ratios, the difference in average distance is not as big. So this was for evaluating how good the reconstruction is. And for evaluating how good the label map is, similar experiments were repeated, but for the F1 score this time. So the F1 score determines how good the label map that has been predicted is. So how correct are the inlier and outlier labels? And you see here that when it's big outlier ratios, then the methods will perform more similar to each other. But when you have very small pathologies, then the proposed method does do a better job to detect them. So the reconstruction and pathology scores do not necessarily have to align with each other. And then we show some results on some challenges from MICAI. The first one is the cranium reconstruction challenge, auto implant 2020. Here you see in green part is a part which has been cut out from the cranium. The orange is the target, so it's missing this green part. The red and blue are the reconstruction with the proposed labels. And for clarity, here is a cross-section of it. So basically what has been reconstructed is the cranium part on top. This over here in green is what the ground truth shape would have been. In red and blue is the predicted shape, where red indicates that this has been detected as missing by the model. And these results are not as good as with the synthetic data. The leaderboard scores have 3.5 and 0.944 for Hausdorff and Dice scores, but with us it's 6.4 and 0.73. But this case, which I'm showing now, is one of the better ones where the results are more comparable to the leaderboard scores, just so you get an impression for what it looks like when it does work. And the next one is the kidney challenge. And in this case, instead of having missing parts, there are some bumps. And so in orange, a bit translucent, you see the target. So it's a kidney, and it has some bumps on it from tumors. And in blue and red, again, you see the reconstruction, where red indicates where the model believes something is incorrect and pathological, and blue indicates where the model believes that there is actually data on the target that corresponds to the kidney. Again, here the results are not state of the art. I think though one reason could be that in the proposed method, actually the label map is on the reference and not on the target, and also only on the surface. So with the kids challenge, these kidneys were actually images in the beginning, and I extracted from them a surface. And so I only detect surface pathologies, while in the paper they can detect inner volume pathologies, so tumors that go like this. So this is more an intensity problem than a shape reconstruction problem. And there was also some results from an in-house data set. So this is a forensics one. And here I've taken from this cranium the mandible part. You see it's missing some teeth, and some part of the jaw might even have dissolved. And here overlaid with the target, you see the reconstruction where the teeth have been detected as missing. There is some shrinking that occurs, but not drastic. Yeah, so with that, I come to the conclusion. The main idea is that outlier detection can be used for unsupervised pathology segmentation, which is pretty cool because it means that you do not need to have labeled data for training, and you also do not need to set a threshold in advance. So basically during reconstruction, the model figures out what is likely to be pathological and what not. And for that, you need a robust regression approach, and we propose the region growing. And you also need the classification threshold, which we propose to do dynamically using the remaining model uncertainty in the GP model. And for next steps, evaluation on the image domain would be very useful, like for the kidney, as I said before, and also different methods to evaluate how good a model is in generalizing and how good correspondence, used correspondence for the section is. And with that, I come to the end. So thank you very much for your attention. If you have some questions later on, or if you want to take a look at the code, you can also let me know.
Thank you very much, Dana, for the very next presentation. Are there any questions in the group?
Hi, Dana. Thank
Hello.
you very much for the presentation.
Thank you for listening.
I was wondering how important this initialization is. So like you said, like, okay, if you take a few points at the beginning, it has to be ground truth. But I was wondering, like, if you take a large set of points at the beginning to get into a nicer optimization area and then actually get the end results, or?
Yeah, good question. Thank you. So mixed answer. The thing is, if you click multiple landmarks instead of just one, then it does not really make a difference because it's an iterative approach. And if you start with only one landmark, or if you start with 10 randomly distributed along this domain X, then eventually you will get to the same solution. But with one landmark, you might need more time to get there, only because you only look at the neighbors every time. But of course, if you take a lot of observations, because this is a discrete model, for example, when you take here a lot of observations, you see that suddenly this remaining variance in the model is going to drop very significantly. And with this very low variance, then you run the risk that all of these observations will always lie above the threshold. And so if you do want to click a lot, you should distribute them along the target, or you should account for ways to correct this remaining uncertainty, which is also current work at the moment in our group that has to do mainly with the model.
Okay.
Does that answer?
Yeah, that's interesting. Thank you very much.
Okay.
I was wondering when Kerem will show up with his phone question, but I guess not so far.
No, I am here actually.
Hi, Kerem.
Hi.
I just couldn't understand this plot here, what you're seeing and so on.
Okay, I can give it another
Maybe
shot.
like in 2 minutes. I'm sorry, but
No problem.
thank you very much.
Okay, I think I will start here. So what you're observing is at the moment a Gaussian process in 1D. Along the x-axis, you have the domain. the mean of this Gaussian process is 0, so it's not plotted, but it's actually just like that at the moment. And the kernel that is being used is a Gaussian kernel with length scale 1. And so when you take some samples from it, they will look like this in the light gray. And for now, I choose one sample, the black one.
So by sample, you mean like, what do you mean by sample?
So this is a sample from the Gaussian process. So in 3D, it would be the actual mandible, the surface in 3D. But now this is just a 1D example,
Okay.
which is taken from this model. So if the model were,
Okay.
So then, so once you have, so this is the target that you want to reconstruct. But instead of having the ground truth target, which is the black line, you actually only have some observations from it. And these are noisy. And so these dots represent those observations which you have and which you can use to try as best as possible to get the reconstruction of the target. So now also you see.
Sorry to interrupt. Yeah. So is that black line and the noisy observations on it, are they like the points of the deformation field of a jaw of some person, for instance?
Yes.
Okay.
Exactly. Yeah, sorry, I guess that was not very clear. Thank you for asking.
No, I think I missed also the very beginning, so I was a bit like lagging in understanding.
Okay. So basically in 3D, each of these would represent a deformation vector that is connecting one vertex on your reference to where it thinks is the corresponding point on the target. And some of them will be incorrect, which are here represented. And this is because the data on the target does not exist, or there is no corresponding point. And so you will have some measurement or some deformation vector value that is not correct. And so you want to avoid them. But you do not have in the beginning these red lines, which tell you very nicely where they are. So you need to get it during fitting. And so then the next step would be you provide one observation. And in this case, it would be one landmark, which you click on your mandible, which you're sure is healthy, or which some method has told you that this is a healthy one. And using this information, you update your shape model. And here in 1D, it would mean updating the mean and the kernel that is used in the GP. And so here you have a new mean in green, which is what, based on this information, what is the prediction of this observed value, observations over here. But you've only conditioned on one, and that is why it looks very bad.
And what are the blue points?
So the blue points are the ones which satisfy the threshold. So then once you use the remaining Mahalanobis distance at the black points, you get a threshold. Using this threshold, you decide which of the remaining black points satisfy the threshold. So which of them are below this distance value.
I see. I see some other observations, like in this like this parabolic place where they are also pretty close to the target, but they are not labeled as inliers. But because the reason is that they don't fulfill, they are not in the threshold. Okay.
Yeah, I think also one thing is that this is, so you don't usually have this target. So the distance that is being used is actually the distance between the black dot and the green line.
I see.
Yeah, because the green line is the current guess.
The black,
yeah, exactly.
Yeah. Okay, thank you very much. Okay.
You're very welcome. Yeah, and what's additional in the mesh is that we also use the connectivity. So then you only evaluate neighboring vertices. And this is to avoid these faraway ones from being labeled too early.
And then you add a couple of landmarks.
So then once you already get, so you need to click some in order to have your first update. Then once you decide that these blue ones, okay, I will include as inliers, then you update your model based on them. And then because you have a new set of blue points, you can get a new set of Mahalanobis distances. So then you update the threshold and then you evaluate the points which you have not yet considered. And you keep on repeating this process. So you update the observations, you update the threshold, again, you update the observations and the model, and you repeat. So what this would look like on the mandible is you would have some landmarks which you've clicked, and then if you click here, for example, you would see in the next step that it grows all the way to here. And if you click a landmark here, then it would sort of grow around this tooth until eventually they connect to each other.
I see. And how does this not like converge to a very, very small threshold? Because you choose the landmarks, and you can choose a landmark which also has a high Mahalanobis distance, so that would even increase the threshold, for instance. So you can,
Yeah.
I see.
Every time you have a new, so when this remaining variance decreases, the Mahalanobis distance is actually increasing because you're weighing the, you divide the distance by the remaining variance. And so every time the Mahalanobis distance will actually increase the threshold instead of decrease it.
I see. It's a very ingenious idea. Thank you.
Thank you.
Now, after this discussion, I'm wondering if it makes sense that if you have a GIF which shows the evolution of your reconstruction over the iterations, then that really shows what you were talking about in the mandible, right? You start at one point and then the blue region starts growing, no? Is that what happens? Am I kind of visualizing it?
Yeah, it is what happens. That's a good idea.
And the red one is at the end, you take the reconstruction error, and that's if that's greater than the threshold.
Yeah, so in the beginning, all of it is red except for the landmarks that you've clicked. And then the red will decrease into what regions are not used, and the blue will increase.
And,
so at the end,
sorry, go ahead, Mira, sorry.
So at the end, so what's still left as red was never within the threshold.
Exactly, right? Yeah.
And how do you decide when to stop? Because you could then also select a point within the red region as one of them.
Yeah, so it stops when, so when we move from this step to the next one, we had here only one, and then we included all the blue points. So now we have, let's say 10. At some point you will get to a point where you reject all remaining observations. And at this point you have no update in the size of your blue region. So the number of these black dots is the same, and then it stops on its own. So it actually does not use, it doesn't evaluate how good the fit is at the moment to stop. It just stops when no more points are included in the blue region.
So you, like the user introduces landmarks only at the very beginning, right?
Yes.
Yeah.
And you, regarding that, you also mentioned you can also have methods that identify these landmarks automatically. Is this something you do as well, or?
I don't know, but I think this would be something that would be interesting to look at. So you could already get different correspondence metrics from curvature, for example, or you can have some methods that get landmark. You give it an image, it gives you some landmarks, which it thinks are healthy. I have not really looked into it for cases where the target is also pathological, because I think usually you start with an image which is healthy and you get landmarks for it. So I don't know if you have an unhealthy image, how some out of the box methods would perform, but that would be something you can use instead, yeah. But the landmarks are anyways used in the beginning for alignment as well. So it doesn't require a lot of extra work, but if you have them automatic, it would be nice, yeah.
I see. Can you also do the converse of it and like do a right click or left click or whatever and say like this is definitely an outlier or something like that?
I haven't thought of it. Yeah, maybe, I guess you can correct. I need to think a bit more to think of how the threshold would have to be changed or what rule you would come out from that. I guess the easiest would be if you already give it some region which you think might be pathological and you reject any points which are updated to inliers there. But if it's easy to get the map, then you don't need to use this method because you can also just use an already labeled surface which tells you which regions are pathological and get a fit.
And also, just out of curiosity, like, I assume this makes like the clinical practice a lot easier, right? Like, instead of someone like segmenting all those voxels, meshes, whatever, you can just do it with a couple of clicks, so to say.
Yeah, exactly. The only thing that's needed for clinical though is you have to actually get a surface. So with bones and CT, this is easy because you can threshold it. You threshold the image, then you know how to build your mesh. But with the kidneys, for example, this still needs someone to actually extract a kidney surface from an image. So it depends on the target. I think ideally you would want to start from an image for the kidneys. Then you completely avoid having someone label every slice. But for bones, it's easy.
Yeah. I mean, if you do it on images, it also reminds me a lot of this scribble segmentation stuff, right? Like where you click on a couple of pixels and say, this is, I don't know, class A, this is class B, and then it grows. And they're using the MRF is also related to the Gaussian kernel, which you use here probably. Thank you very much.
I would need to look there to see how they get also exactly a threshold and such. Yeah. But the region growing is definitely the same idea.
Cool. Are there some other questions?
Oh, I cannot hear you, Georg.
Is it getting better? Is this better now?
Yes.
Oh, sorry. Yeah, I did wonder one thing, and maybe you already sort of answered it, but so that the data structure you have is sort of this mesh where you not only have vertices, but also connections. And then I wondered, you have the Gaussian process you have over the deformation field. So I wondered, you get reasonable deformation fields, but this might give unreasonable meshes, right? Especially for the teeth, where maybe there are two teeth surfaces and then the deformation makes them like this. So then the mesh is sort of messed up. I wondered if this is a problem, or maybe.
Yeah, so it's not a problem. I think if I understand your question correctly, because actually the deformation fields are defined from the reference. So every vertex on the reference is associated with a point on the target. And so you have as many deformation fields as you have vertex numbers on the reference. And so the number of vertices in the meshing of your target does not play that big a role, because when you find the corresponding point, it's usually closest point from the reference vertex to the surface target. And it doesn't need to identify, it doesn't match every point on the target to a point, every vertex on the target to a vertex on the reference. Does it make sense somehow? Can try again. So this deformation field, you see here vectors, and the vectors are defined from the reference to the target. So you have as many deformation vectors here as you have number of vertices on the reference. So now if you want to find this deformation vector for a new target, which has a different number of vertices, what you do is you start with a vertex on this reference mesh, and you find the closest point on the target surface. So this is, it does not rely on the vertices of the target. So you can even find a point between two vertices and you measure the distance between that point and the vertex on the reference. So the deformation vectors,
I think this I see. Yeah, I think it makes sense. I think it makes sense. But maybe, and yeah, I'm still not sure. Could you, if you pick a seed at a very unfavorable location, let's say at some tooth, and this tooth is very close, like on the to another one in the target, and maybe it's not clear which one will correspond to, right?
Yeah, exactly. So the correspondence function here would play an even major role. So I just use the closest point correspondence, but I think if you have a lot of fine details and you do not want to miss the correspondence, then you would have to use something like curvature, and then you would make sure the top of the tooth. So it really depends on the correspondence function.
Makes sense.
But I think because the correspondence is updated every time you have a new mean from your models, so you have different reconstruction every time, then this sort of avoids the problem of making a very bad correspondence decision in the beginning.
Yeah, I think I see. Thanks a lot.
Thank you.
If there are no further questions, I'd like to, I mean, in any case, I would like to thank Dana for the very nice talk and for answering all these questions. And I personally learned a lot. I also learned why kidney beans are called kidney beans now by looking at the shape of the kidney. So a lot of learning.
Thank you. Thanks for inviting me. And thank you for all your questions. It was also useful for me.
Thanks a lot. Okay. Bye-bye then.
Thank you. Bye-bye.
Bye.